So let's do this. If there's no questions from homework stuff, just a quick little review before we get into new stuff. So we started let's do this. Let's do like a rewind. We started with right triangles, and we defined, thank you, Trent, and we defined 6 functions based on the 6 ratios. And at that point, everything we were doing was coming from right triangles. But then, so we defined like sine, like we said, sine of theta is y over h and so forth, all 6 of those bad boys. And you have 3 primary ones, like the 3 primary colors. And then what are the other, what would you consider the 3 primary trig functions? What would you say are the 3 primary trig functions? Sine, cosine, tangent. Now somebody else tell me, why do we consider the primary? What are the other 3? What do the other 3 do?
The other 3 are the inverse.
Yeah, they just flip. Be careful. I'm going to be a little picky. Don't say inverse, because that means something specific with functions. The reciprocals. You're good. Okay. Again, it's just weird stuff we did with math language. It makes it a little hard to talk about it. So we got sine, cosine, tangent, cosecant, secant, cotangent. Yes, and we've worked with those. If I give you a triangle, you could just eat that up. Yes? I think we all agree. We've done enough of that. Then I looked at equilateral triangle to help us figure out some specifics. I want to know sine as a function. It should not need a triangle. It should be able to exist on its own. I should have an input and then there's an output. So then we figured out, for example, what's the sine of 30 degrees? 1/2. Please remind me, and forgive me, because I'm teaching this exact same stuff in my other class. I did give you the way to kind of think about it so that you don't have to memorize it directly. What is sine like? Is it like x or y? Y. So sine gets bigger the closer to y. It's kind of like this is home, so the turtle comes out of its shell, the closer it is to home. So when I'm at 30 degrees, am I close to the sine home? So it's scared, it's going to be the smaller possible output, that's 1/2. Right? What are the 3 main middle outputs? Like, what's sine of 0? That's an extreme. 0, why? Why is sine 0, 0? It's all what? Not any of this, it's all x, and sine measures y. So the 0 y piece to the x-axis. So of course here it's 1. In the middle, what are the 3 possible values it could have for the angles that we're memorizing?
30, 45, 60.
Those are the angles. What are the outputs it has? 1/2. Rad 2 over 2? Rad 3 over 2. So it's kind of nice. 1, 2, 3. Yes? So here's what I think. I still do this to this day. I have not got sine of 30 degrees memorized. I don't. I just do this very quickly. I go, 30 is closer to x, sine likes y. It's the smaller output, it's 1/2. And of course I do that pretty quickly, but that's basically what goes through my head. I don't want to memorize shit. I don't. You can't make me, damn it. So sine of 30 is 1/2 because sine hasn't grown very much yet. It's really close to x, it's not close to home. So what is sine of 45 degrees? And that we proved from the 45-45 isosceles right triangle, right? We actually proved it. We proved that sine 45 is rad 2 over 2. And then what's sine of 60 degrees? Rad 3 over 2. And of course that was coming from that first guy, yes? And then of course, cosine does the opposite. It starts off big. It starts off in home. So it loves it here. So what's the cosine of 0? because all of it is x. 100% of it is x, so cosine is 1. And then as it moves away from home, it starts to shrink. The shadow on my arm is getting smaller and smaller from the overhead light. That shadow is cosine. So what's the cosine of 30 then? It starts off at 1 and then shrinks a little bit. So what's the cosine of 30? It's still close to home. Root 3 over 2, this slightly bigger middle option, yes? Jeff. So this will be root 3 over 2. Of course, at 45 degrees is where they both equal each other. And then, of course, at 60, it's really scared. It's pretty far away from home. 1/2. And, of course, at 90, can't even say it's scared anymore. It just is like totally incapacitated. What's cosine of 90? 0. Good, because no part of the y-axis is along the x-axis. It's all y. So cosine hates it there. Sine loves it there. Sine of 0, same idea. Get out of there, 1. Cosine of 0 loves it there. Okay. Okay, good. So we built all of this stuff up. And then did I show you the pattern, right? The square root of 0 over 2, square root of 1, okay. And then I think we did a handout that had like a specific, was it the radio tower?
Yeah.
Okay, good. That's really important because that is really simple. That is a very simple problem, but it's an immediate thing I can do in the real world. Immediately. So if you had a way to measure the angle and you had a measuring tape, you could see how tall a really tall ass tree is without having to climb it by just walking away until you hit like 30 degrees. Because that's the thing we know. And then you can actually figure out how tall it is. You guys coming with me? I mean, that's silly. This is relatively kind of advanced math, but it has an immediate application that would be relatively easy to do if I get decent angles. If my angle was 11 degrees, screw that shit. I don't know freaking sine of 11 degrees. I'd have to use a calculator for that. But if I can make it an angle I know, I can do stuff with it. Okay. All right, let me stop for a minute. So, I think, let me think for a second. You guys are going to have to forgive me. I'm an old man. I want to make sure I've covered the other stuff. Let me see. Today's been crazy, by the way. I'm sorry. Let's see. So 7. Yes, okay. Yeah. We did everything. Look at us go. So the book is kind of silly. By the way, when I read this, all I saw was this. And I'm like, that sounds like a horror movie. The other. But the other trig function. So it waits until 7.4 to talk about secant, cosecant. I just did that from the beginning. So when I first talked to you guys, we did 7.2 and 7.4 when we first started doing chapter 7. 7.3 is unit circle. I don't use it that much, but I have drawn it quite a bit. But I am never going to give you a blank unit circle and make you fill that damn thing in. Okay. Because my own reasons. I think most of my colleagues do, and I still don't understand what the utility is of that. Maybe Christina can explain to me if you I don't know how you feel about it. Do you agree with me or no? You don't have to agree with me. Nobody has to agree with me, ever.
I don't like the blank units here.
Thank you, okay. Not because it's hard, not because of any of that, because it doesn't help to do anything. That's what really makes me go crazy about it. Okay. So, now that we've established how trig works by itself, we know sine, we know cosine, we know all this stuff. We know if I give you a triangle, you can set up the ratios. If I give you a tower and certain things, you can figure out how tall the tower is. You can do all that stuff. Now I feel comfortable to go back and give another layer of new thing. I think I said this already. Like 7.1, we're going to talk about a different way to measure angles besides degrees. And I don't like the idea of doing that and then adding another layer of new shit, trig. Okay, so now we've been exposed to trig by itself. I feel okay to go back and talk about another way to measure angles. So what is wrong kind of with the way we already measure angles? Well, let's talk about why we do it. How many degrees are in a full circle? That's insane. So if I start at 0 degrees and I go all the way around, I've gone through 360 degrees. Yes? Why? Does anyone know why? Have I told you why? I can't remember. Does anyone have a guess as to why? Do you guys, first thing I want you to understand is, did it have to be this? Is there anything about a circle that says it has to be 360 degrees? And in fact, what I'm saying right now is something that students don't often think about, because number one, you got too much other shit to worry about. And number two, you don't even realize it was an option. That was a total choice. I gotta look at the history, because I always forget to look at the history. I know where it came from. Have I talked about the Babylonians at all? I love you guys. You're like, I always stop and think what it would be like to be a student, and your math teacher's just like, oh, we told you about the Babylonians. Like, Babylonians had a base 60 number system. What do we have?
Base 10.
Yeah, I don't know why we have a base 10. Nobody knows why. They didn't have 60 fingers, okay? But they used a base 60 number system because why would the number 360, for example, be important to them? Most civilizations back in the day were what kind of civilizations? What were they most focused on? Agriculture. They were most focused on feeding people. Yes? We still are today, but we got that pretty well down. Although, okay, Jeff, don't go into capitalism, stuff like that. Okay. I'm not going to make an economic theory class. So they like the number 360. They like the base 60 because they kind of like show up in each other and so forth. So I could show you Babylon. I'm not going to. So we stole from the Babylonians the idea of time. Seconds and minutes, minutes and hours. How many in each? 60, 60, that's from the Babylonians. 360 is partially because of that, but mostly it's because, can you factor 360 a lot of different ways? Hell yeah. 36 has got a lot of factors, and then 360 also has even more factors, but it's a nice round number, it's an even number, 6 goes in, so 3 goes in, 9 goes in, you got so many things. Do y'all understand now that we could have made it 400, for example, and then this would have been 200 instead of 180 degrees, and we would just accept it. We wouldn't have any reason to think otherwise, and I would be going up here, can you imagine if we made it 360? Y'all be like, holy shit, that'd be weird. So degrees are completely arbitrary choice. You guys, there's nothing wrong with using degrees, because I can still tell where I am. If I said draw a 70-degree angle, you guys could do it, because we've established all the way is 360. If I said all the way was 400, you could still draw a 70-degree angle, yes? As long as we establish what the whole thing is, I can draw whatever in the middle. But 360 was just an arbitrary choice we made. Now, there is another way to measure moving through an angle, and it's better because it uses a physical measurement of the circle, not this made-up bullshit. So here's a radius of the circle. Yeehaw! My circle does not look amused. R. Now he looks contented. If I pick that R up, right? If I pick it up and put it there. Did I turn you on? I did. There it is, yes? There's R. And then I do the old, like, watch me, and I bend it. Yes? So now I bend the R, and then I put it back on the circle. So how long is this? That's R, yes? Do you see how I've gone through an angle as I did that? So if somebody was walking along the outside of the circle and I just sort of like followed them, I turned through an angle, yes, as I watched them. Are you ready for this? This is kind of silly. How many radiuses did that person walk along the circle? 1. So we call this angle, I don't know why I put an R there. Oh yeah, that's from earlier. We call this angle is 1 radian. where radian literally means number of radii, or like I like to say, number of radiuses. Do you guys see how that's better? That's not arbitrary. It's not just out of nowhere. It's not because we like to factor 1. In fact, 1 sucks. But is this a physical measurement? Is it based on the reality of the circle? Yes. It's not just some, how many slices of pizza do you want? I want 360 euro. You know, where'd that come from? So, one thing to notice, very, very important. I drew this circle, so yay, Jeff, that angle is 1 radian in this circle. What if it was a bigger circle? Well, if I made the circle bigger, doesn't the radius get bigger? Then I go further, and I end up going exactly the same. If I go 1 new bigger radius, it ends up exactly where this angle is the same. That's like that scaling up thing we did with triangles. So this makes physical sense. Okay. So where would 2 radians be? I would just go, well, let's go back to my original circle. I would just go 1 more radius length, so it would be about here. You guys with me? 3 would be about here. So the next really good question is, I know how many degrees are in a circle. How many freaking radians are in a full circle? You guys with me? So to get there, I want to show you a nice little concrete example of what the hell I'm talking about. Let's say I got a circle. I'm telling you that's a pretty good circle for me. It's got a little cowlick, but it's going to be okay. Let's say the radius is 11. Sorry, now it looks like a little video game character. 11, we'll say 11, just to step outside of our country for a second, 11 meters. And I have somebody who walks, let's say, what do you got, Jeff? 26 meters. Can anyone figure out what that angle is in radians? Come back. Go away. Come back. Come back. Huh? Well, first off, let me just ask you, what would you do to figure it out? Okay, pretend like I would have said 22 meters. Why is that an easy question? If I went 22 meters, how many radiuses did I go? 2 of them, yes? Because every one is 11. So if I give you an ugly number, 26, poor little 26, how do I figure out exactly how many radius this is? 26 divided by 11, right? So what's a radian? Why do we call it radian? How many radiuses I go around? Yes? So if I said 3, I have an angle that's 3 radians, that means I just go 3 radiuses across the circle. That equivalent amount of length. Are you guys with me? Radians kick so much ass. You're not going to like them at first because they're going to look a little weird and you're not used to them. But it is so much better. So in this case, the angle is going to be in radians. It's going to be 26 meters I went divided by 11 meters each radius. So if you put that in the old calculator, what are you getting in? 2.36? Blah, 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 blah. And officially that would be radians. So this would represent 2.36 radians laid down on the circle. That's how that distance is. All right, how are we doing so far? Radians are, hopefully, the idea behind them is really simple. Almost too simple to believe, and then somebody should be like, well, why do we ever talk about degrees then? Why don't we talk about this thing? I agree. Now, a couple things. I'll finish this out, but there's an interesting formula that's hiding in here that we just did. We didn't even realize it. Look at us, we're that good. So if I want to go all the way around a circle, I'm not even going to tell you what the radius is. Can anyone tell me How far is it away? How far is this to go around this happy little circle, dude? How far is this?
6 radians.
Oh, I see what you're trying to do. No. Not the angle, I want to know the distance. How far would I walk if I walked around that circle? What's that called? If you go all the way around the circle, it starts with the C. Circumference, yes. It's the knight conference who got knighted, so now the circumference. Excuse me for that. So, does anyone remember the formula for the circumference? Do it again. Alright, real quick. Pi r squared would have square units. What do we measure in square units? Area. With me. So pi r squared is the area of the circle. And of course pi are round, but not square. No. Does anyone remember the circumference formula? Yes. And real quick, did I ever tell you about where pi came from?
No.
Okay. So many guys would be like, Marie Callender. So, back in the day, several civilizations realized if I take any circle in existence and I measure all around it, and I divide that by its diameter, I always get the same number. Several civilizations on their own discovered this because they didn't have Xboxes or Instagrams. So they're like, let's just play with circles, okay? But I don't care how big the circle is, I don't care how small the circle is. And do you understand this would freak people out a bit when they realize if I measure all the way around and divide by this, I get the same number every time? That's a little freaky. So, not surprisingly, they gave it a symbol. And to be honest, we gave it a new symbol, but that's okay. We call it pi. The Egyptians estimated it to be 22 divided by 7. Does somebody have a calculator right there? What is 22 divided by 7? It's pretty good.
1, 4, 2, 5, 4.
Yeah, and you all should know the first 3 numbers of pi, yes? 3.14. Which if you write 3.14 a certain way, it looks like the word pi reflected. Have you guys ever seen that? Maybe I'll show you. So, real quick. Pi came from the fact that when I take a circumference divided by diameter, I always got 3.1415, blah, 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 blah. Always. So therefore, look at this. This is kind of silly. What's the circumference formula? Multiply by d. So circumference is pi times diameter. Now, I want things in terms of radius. What's the diameter in terms of the radius? Yes, diameter is twice the radius because it goes all the way across instead of stopping in the middle. So if I replace d with 2 radiuses, then I'm at 2 pi r. Okay. Is everybody with me? If I went all the way around this circle, how far would I go? 2 pi r. Beautiful. So remind me, when we had a problem up here and I told you how far somebody went, how did we figure out what the angle was? We took the distance they went. We took the distance they went divided by the radius. So here, what'd you guys just tell me? If I walked all the way around, how far did I go? 2 pi r. And how long is the radius? So how many radians are in a circle? 2 pi radians. Radians are the number of radii as I move around the outside. How many radii fit into how far I've gone? If I do 2 pi radians, I don't care how big or small the circle is, I'm going to end up back at the beginning. That's kind of neat. So remind me, so what have we got so far? 2 pi radians is the same thing as how many degrees? 2 pi radians is the same thing as 360 degrees. Do you guys agree with me that 24 inches is the same thing as 2 feet?
Yeah.
Why wouldn't I use that as conversion? 24 inches is equal to 2 feet. Why is that not the best conversion to use? It's not reduced. What do we use to convert between inches and feet? Is the fact that 1 foot is 12 inches. Do you see up here I got 2 pi radians is 360, so how can I reduce that? If 2 pi is 360, 1 pi is 180. Okay. The same, no. Let me stop for a minute. Let me take stock. Is everybody doing okay? How many of you guys have heard about radians before today? Anybody? How many of you guys are pretty sure you've never heard radians before? Anybody? You've all heard about radians before. Have you never heard about radians? Does it make sense? Thank God. I don't know if you just tell me that or if it really makes sense. Okay. Radians are really nice. The numbers are kind of sucky. The fact that pi is there is kind of sucky. But the idea of them makes immediate physical sense. Let me stop for a minute. Now, the same way that I can convert between feet and inches because I know 1 foot is 12 inches, we can now convert between radians and degrees because we know this. So, I steal something from chemistry. Who's taking chemistry? Anybody? Do you guys remember unit analysis? All right, don't worry. We're not going to do Avogadro's number. We're not going to do Pivnert. We're not going to do ideal gas. Okay. Let's say I have 30 degrees, and I want to know how many radians that is. So if I start with 30 degrees, what unit do I not want anymore? Do you guys, what units is this already? Do I want degrees? No. So where would I put degrees so that the degrees would cancel? Would I put it on the bottom or the top? Where would I put them so that they will cancel? On the bottom. If I put them on top, I get degrees squared. I don't want degrees squared. I don't know what the shit that is. So if I put degrees down here and radians up here, now I know where to put my numbers. How many rads is how many degrees? What am I drinking?
1 rad.
Oh, man. Oh. Yeah, be careful. How many radians is how many degrees? What did we just say? Pi radians is 180 degrees. Yes? Can I reduce these numbers? The degrees cancel, yes? I can kill a factor of 10, yes? 3 over 18 reduces to be 1 over 6. So this becomes pi over 6 radians. So if somebody says 30 degrees, the angle is 30 degrees, somebody else could say, oh, that angle is pi over 6 radians, and they're talking about the exact same measure. Pi over 6 radians is 30 degrees. The same way that 24 inches is 2 feet. Yes. So what would I do if I knew, this one's kind of silly, what if I had something that was in radians and I want to convert it to degrees? Let me do it the long way and then I'll show you a shortcut. So I've got pi over 9 rads. What unit is there that I don't want anymore? I don't want rads, right? I want degrees. I want to kill rads. So where am I going to put rads? On the bottom. So of course on the top I'm going to put what I want. These die, go away, you're dead. How many radians, how many degrees? What goes here? How many radians is how many degrees? Doesn't change, it's always the same. 180 degrees is pi radians. So what happens here? Die. And then what's 180 divided by 9? 180 divided by 18 divided by 9. Add a 0, yeah, 20. Now here's a shortcut. If I have radians and I want degrees. Well, pi radians is 180 degrees. So I actually, if I have radians and I have a pi in there, I can just replace it with 180 degrees. So converting from radians to degrees when there's a pi up top kicks so much ass. How you guys feeling? You guys all right? Okay. Now listen real quick. Okay, it's like, my entire life? No. This by itself is very different from what we've been doing. But I want you to realize what's going to happen now. How is this going to integrate back into what we've been doing? Can you guys remind me? Well, let me do it like this. You ready? What's the sine of pi over 6? Is it in degrees? How do you know? Don't say because there's a pi, because I can say pi degrees. There's no degree symbol. If there's no symbol, it's radians. So if you're writing an answer to a question and you say 7, I'm assuming it's radians. If it's supposed to be degrees, you're going to assume. So if you don't put any units, it's assumed to be radians. If you put degrees, then it's degrees. We know what this is from just a moment ago. Yes? That's 30 degrees. So sine of pi over 6 is sine of 30 degrees. And what is sine of 30 degrees? Yeah, 1/2. Because sine likes y, 30 is closer to x. It doesn't like it there, it's smaller. Kick ass. I love it. Now listen, radians is brand new to some of us. In terms of this course, it is brand new. You need to, I'm going to try to get you to work directly with radians more often because you need to get used to radians. But you guys understand the reason I did this out of order. We have to learn trig and we have to learn radians. I didn't want you to have to learn both of them at the same time. Okay. I could be wrong, but who knows? So, remind me how to do this problem. Let's go back to degrees for a second. What would the first step be in this problem? Reference angle. And how do I find the reference angle? So, what is it in reference to? Why do we call it reference angle? It's in reference to the what? X-axis. So whenever I give you something like this, you're outside of the first quadrant, it's got to be based on the reference angle. Because we only have first quadrant degrees memorized. 150 does it get all the way back to the x-axis? Okay, so normally with reference angles, you either pass it or stop short. And the amount that you stop short or pass is the reference angle, period. That's all it is. How short did we stop from getting back? We stopped 30 short because all the way would be 180. So the reference angle is 30 degrees. Cosine, what's true about it here? Oh, so, yes. I'm sorry. What's true about cosine where we are? It's negative. And the answer is going to be the same number as 30 degrees, yes? Because this is the exact same triangle that could be over here. It's just got a negative x side length. So the number answer to this is the same as the number answer to this. It's negative just because I'm somewhere where x is negative. So if you know cosine likes x, you know when it's negative. Sucker, don't do that for me. Okay. What is cosine of 30 degrees? Yes, because cosine likes x. 30 is closer to the x-axis. It's bigger. Yay! Okay. So, help me out for a second. What does this look like in terms of radians? I'll start. 0 radians. Thanks, Jeff. Who knows what goes up here in terms of radians?
1/2 pi?
Exactly. It's 1/2 pi. right? Because we already know what's over here. That's the conversion. What's 180 degrees? Pi. So this must be half pi. And of course, what is half pi? Pi is 180 degrees, so half of 180 is 90. That's where 90 is. Cool. What's this one? So that's 1 pi over 2, 2 pi over 2. Is that cool? 3 pi over 2. Because every little quarter turn is 90 degrees, so that's going to be... Why are you putting it there, John? I don't know, man. And then if I get back here, I've gone through how many radians? No, 2 pi. So real quick, can you guys estimate where 3 radians is? What quadrant would 3 radians, an angle of 3 radians live in?
2.
Why? You're right, but why?
Because a radian is, sorry.
You're fine.
I don't know.
Real quick. What is pi roughly? 3.14. So if I only go 3 radians, I stop short of pi, right? That's probably what you're thinking in your head, but then you're starting to overthink it. I don't care about it's the number of radians. I actually can just compare it now that I've got these anchors. I can see. So didn't we just figure out like a way to get a reference angle in radians? Real quick, watch this. What if I had to figure out what sine of 5 pi over 6? No. Sine of 7 pi over 6. There we go. That's what I want. What the shit, Jeff? So real quick, why was 150 easy? Because I could tell I stopped short of 180, yes? Well, now what am I looking at? I'm looking at pi. That's closer to pi. Did I go past a full pi, or did I stop short of a full pi? Yes, why? Because what's a full pi? How many sixths is a full pi? 6 sixths. This is okay. So this, if I wanted to, and now it's really easy to tell how far did I overshoot this. If I go 7 pi over 6, how far did I overshoot? Sorry. A little bit. How far exactly? 1/6, not 1 radian.
1/6 pi.
1/6 pi, right? How far past 6/6 pi is 7/6 pi? 1/6 pi. So the reference angle here is pi over 6. So this, what's true about sine in that quadrant? What sine, S-I-G-N, is sine in that quadrant? Why? Because the y is negative. I love it. I love when I say y. I'm sort of answering it for you. And then, so it's negative. And then it has the same value as the sine of pi over 6, which we did just a second ago. What was the sine of pi over 6? Because what is pi over 6? What is it in degrees? 30. Because it's just 180 divided by 6. What's pi over 6? I'm sorry. What's pi over 3 in terms of degrees? Pi over 3 radians. 180 divided by 3. 60. What's pi over 4? Here's how you do 180 divided by 4 real quick. What's 180 divided by 2?
90.
And what's 90 divided by 2? That's 180 divided by 4 because we cut it in half twice. So 45. And let's see why that makes sense. Which one's bigger, pi over 6, pi over 4, or pi over 3? Which one's the biggest? Why is that the biggest? Because it's the one that I'm dividing by the least. When I divide by smaller, my answer gets bigger. Yes? So it kind of makes sense that 30, 60, 90, pi over 6, pi over 4, pi over 3. Because as I divide by less, it gets bigger. Okay. Okay. I want to make sure that I do everything I want for this handout I got for you guys. Here we go. Oh yeah, that's right. We got a few more things to talk about. So now we know how to convert between degrees and radians and vice versa. What is? Let me see if you guys are cool with this. We actually know the formula for this already. So let's say that I go through some angle. By the way, the official word for this, if I walk around the outside of a circle and there's an angle that I somebody would turn as they watch me, we call that I subtended this angle. Can't remember if the book says it, but this is the angle subtended by me walking around the edge of the circle. I think the book says subtended somewhere. No homework problem, but just in case they do, all that means is the angle is in the middle as you walk around. I want to know the arc length, meaning this distance. So this distance here is called the arc length. I want to figure out a formula for it. We actually did this earlier kind of backwards. What does theta mean if it's in radians? Okay, fundamentally, what does radian mean? How many arcs? How many radiuses is this? Yes? So help me out. Let me give you a concrete example. If I had a circle of radius 5, and we go 4 radiuses, how far did we walk? If our radius is 5, let's say 5 feet, and we go 4 radians around, how far did we walk? You can do it. What does a radian mean again? 4 radians, what does that mean? What does radians mean again? Number of radiuses, or however you're saying it. How do you say it?
How many times you go around the circle?
But you have to bring in the fact that it's a number of radiuses. That's the important thing. So how many radiuses worth did this person walk? 4. And how big is each radius?
5.
So how much total distance did they walk? 20 feet. So if I want to know the total distance walked, I would take theta 4 times r 5. Get 20 feet. So what can I do in general then? Because if I would have made this different and this different, we would have done the same thing just with those different numbers, yes? So what do I do in general? I would take how big each radius is times how many of them. Now, what variable do we use for arc length? Well, kids, obviously, I'm going to use S. No, it's not obvious. So arc length, we use the letter S. That means arc length. That is the formula for arc length. Okay. I love you guys. Not arc raters, just arc length. What I could also be, and real quick, just to really put a fine point on this. Let me give you a concrete example. See what you guys think. So everybody's got that formula down? You with me? Okay. So what if I had gone through an angle of 48 degrees and my radius was 3 centimeters? What would you do? Why? So real quick, I could understand if somebody would do 48 times 3, and that's way too much. Yes? That's way too big. I mean, I think just by looking at it, I could tell it should be roughly equal to 3. Is that, you know? You guys kind of with me? So here's the reason. Why does this formula work? Why does this formula work? Because if the angle is in radians, radians means the number of radiuses. So what must be true about the angle then if I want to use this formula? It's got to be in radians, because it's got to be a physical idea, not made up degree bullshit. So the important thing here is theta must be in radians. So what do I have to do here first then? Like you said, Trent, I have to convert 40. How do I convert 48 degrees to radians? Yes, you make a little grid. What unit goes on the bottom? Because I want those to die. Die. How many radians in how many degrees? No, one. What am I? Pi radians in 180 degrees. Now, real quick, watch what I'm going to do. You ready? The arc length is radius times angle. And I'm just going to throw all that in my calculator. Because the question wasn't convert 48 degrees radians. The question was, what's the arc length? So I don't care what 48 pi over 180 is. I'm just going to throw it in because it's the angle. What is that going to be, Jeff? Let me see. 2.58, maybe? Did I do that right? We'll find out. Bless you. My guess is 2.58.
2.5.
What is it?
2.5.
2.51?
Yeah.
God, I suck. 2.51 what?
3274.
No. It's okay, we'll round to here. 2.51. No. Centimeters. Yes? By the way, real quick. In here, what's the only units? Well, all right. How do I say this? Radians isn't. How do I say this? Radians is the number of radiuses. In a sense, it's not really a unit, because it's just kind of like the number of radiuses. So when I have 3 centimeters, that takes over. So radians just kind of move out of the way for the new unit of centimeters. And again, this would be in radians, which means number of radiuses times 3 radiuses. So the radiuses sort of like cancel out. And that's why you end up with just centimeters. So if I'm measuring length, I should end up with length units. Okay. Now, last little thing before I can give you something to work on. The next thing we can do with like little slices of this pizza. So let's say I have this. Let's say I have, what do you got, Jeff? 4 pi over 3 is the angle. And the radius is, you could do it, buddy, 10 inches. There we go. In this case, I don't care about the arc length. I care about the area. I want to know the area of that. And the word we use for this is we would call this a sector of the circle. And it looks like sunrise over a very well-defined cliff edge here. Okay. But you guys with me? So I kind of shaded in the area that I want. So I want to build a formula for this. So let me make a slightly easier to look at example. What if I took a slice of pizza and I just take this little dude and I plop him down here? Is everybody cool with what just happened? How tall is this slice? Like here. Don't overthink it. From the center to the outside is R. Is everybody with me? What would this length be here? I kind of gave it away there. How long is this piece? Do we have a formula for that? What is it? If I know the angle in radians and I know the radius, how do I get the length that I've gone through? R times theta. Yes. So this is R theta. Now, there's a whole thing I could do with proportions of crap. I hate that shit. Do you guys agree this is almost a triangle? Why is it not a triangle? Because one side is curvy, yes? What's really neat is if I let theta get really small, this essentially becomes straight. It's sort of like if I zoom in, we're standing, I'm a little scared. Does everybody agree we're standing on a globe? Does it look curved? Why? We're on a globe. Why does it not look curved?
It's large.
Because we are right on it, and it is large. It's large. So the curve, when you zoom in on a function, it becomes straight. And you zoom out, then it starts to curve. But if you're really zoomed in on it, you're only going to see a straight line. So here's the really cool thing, just to truncate this whole discussion. If I treat this as if it was a triangle, what's the area formula for a triangle? So if I have a triangle with a height and a base, does anyone remember the area formula for it? So let's see, let's develop it. You ready? What if I had a parallelogram? The area of this parallelogram would be base times height, because do you see how I could take this triangle and put it there, and then it becomes a rectangle with a base of b and a height of h? So the area of the parallelogram is base times height. How much of that is this triangle? How much of the whole area is this triangle? I just cut it in. I cut this whole rectangle, I cut it in, not rectangle, parallelogram, I cut it in half. So the area for a triangle is 1/2 base times height. In this guy, if I pretend like it's a triangle, what's acting like the base? Yes, this is acting like the base. So it'll be 1/2 base, and what's the height? R. So the area is 1/2 r squared theta. That is the actual area for a sector of a circle. And let's double check. Does somebody remember earlier? Somebody had the guess that was too early, but now it's time to bring it. What's the area of a whole circle? No. Not the amount of degrees in it. What's the area of a circle? Pi r squared. Now come at me with how many total radians are there in a circle? How many radians in a circle? 2 pi. Okay. If I plug 2 pi into this will give me the area of the entire circle, because 2 pi means I've gone all the way around, correct? So if I plug 2 pi in here, what do I get? 1/2 of 2. So I get pi r squared. Sure enough, if I use this formula and I plug in the entire circle, 2 pi, I get the right formula for the whole circle. And if I plug in a smaller measure, like what I have in that problem up here, is my angle good to use? Why? It's in radians. So I got area is 1/2 r squared theta. What's r? So what is it? 10. And the angle is 4 pi over 3. So if you plug that in your old calculator, if you have one, let's see, Jeff, what do you think it's going to be? It's going to be like, I never go far enough. I'm going to say 211. Do I went too far? It's probably less than that. All right, cool. All right. 209.43. Okay. What would the units be? No. No. inches squared. For two reasons. We squared the inches. Also, it's area. Area is always square units. Area is literally how many squares will it take to cover this. That's what it is. Volume is how many little cubes do I have to stack to fill this room. So that's why volume is cubic meters, or cubic units. Area is square units. Length is just units. Okay. So let me finally, dear God, shut up and let you guys try some of these out. I'm gonna. Boy, is it an earthquake? There we go. All right, guys, let's take a look. So I'm in degrees. So where should I put degrees? Down. I like it. So the degrees cancels. So up top goes pi radians. Now, real quick, I just want to point this out. Does everybody agree with me that pi radians equals 180 degrees? They end up at the same place, so they're equal to each other, yes? So what is pi radians divided by 180 degrees? Don't overthink it. Are these the same thing? So what do you get when you divide them? So when I do this, I'm multiplying this by 1. I'm multiplying it by a very specific 1. So that's why I'm allowed to do this. I'm not changing the measurement. I'm changing the words I use to describe the measurement. So it remains the same measurement because I'm multiplying by 1. But I'm changing the units that I'm using. So, I mean, real quick. This helped somebody else out. If I have 40 inches, how do I convert that to feet? I put inches on the bottom and I put feet on the top. How many inches, how many feet? 1 what? 12 inches, 1 foot. Then I would just do what with these numbers? All right, that's the step I often forget, and I apologize. To me, I don't even think about it. I'm like, 12 is on the bottom, so I'm going to divide. This is literally 40 times 1 divided by 12. So in my calculator, everything on the top you multiply by, and everything on the bottom you divide. So if I had, real quick, if I had some long freaking thing, and they had this, in my calculator I put 7 times 11 times 2 times 4 divided by 5 divided by 100 divided by 9, and let it spit out the answer. You guys with me? Everything on the top you multiply, everything on the bottom you divide. That's the beauty of this kind of grid method that I kind of stole from chemistry, but they actually stole it from us first, so it's okay. Now this, I don't ever want, if there's a pi there, I don't want you to multiply by pi. I don't want to make it this big freaking decimal. And you'll see why the further we get into this. I want this as a reduced fractional part of pi. So how do I reduce 240 over 180? First thing I do is just kill the 0, yes? Die. Now, real quick, here's a really cool little trick. In this case, the trick works perfect. Bless you. How far apart are 24 and 18? They're 6 apart. So either 6 goes into both, or a factor of 6 goes into both, or none of that goes into both. So either I can divide both by 6, or I can divide both by 3, or I can divide both by 2, or they're both relatively prime to each other. So I can divide both by 6. So if you're looking at a fraction, you're like, I have no idea. Take the difference of the two. Divide by that. If that doesn't work, divide by a factor of that. That's a really cool thing to realize. Very quickly. Why does that work? Because if these reduce, that means at least a part of them is in the same line of multiples. 3, 6, 9, 12. So aren't these in the list of multiples of 6? If 6 didn't go in, they would maybe be in the line of multiples of 3 or the line of multiples of 2. Okay, maybe. So in this case, I can divide both by 6. So I end up with 4 pi over 3. And you can either write rad or you can just leave it blank because I'll know you mean radians. So be very careful. If you write 30 and you meant 30 degrees, you're going to lose some points. Because if you just write 30, you're telling me 30 radians. Yes? Okay. There's a shortcut and a long cut for this. I'll do the long cut first. So this is radians, yes? Radians. So where do I want radians to go? Down. And on the top I put degrees, pi radians. These cancel. So then I do, what's 6 into 180? And then 5 times 30? So 5 pi over 6 is in the same place as 150 degrees. And very quickly, what is this in radians? This is how many radians? That's pi. So 5 pi over 6 should be about right here, yes? I'm like pi over 6 short. And where would 150 degrees be? About 30 degrees short. So you can see visually, that should make sense. They're about in the same place. They're actually exactly in the same place. Okay. Just two different ways to measure the same thing. Same way we have feet and inches, and then we have meters and centimeters, like all those weird, every other country in the face of the earth uses, yes? So now you have degrees and you have radians. You have two choices for how to measure angles. What is part C currently in? What units? Radians. So I put radians on the bottom, degrees on the top, and this is one where I would just let you just plug all this shit in the calculator because you're dividing by pi. Forget about it. So I don't know. You got 600 something, maybe? 6. 630?
Yeah.
Point stuff?
25.
All right, I love it. And we'll say that's what units? Degrees. Beautiful. I love that Ronnie said it's degrees, man. Yeah, because we killed the radians. And then the last one is just like the first one. 330 degrees. Pi radians 180 degrees. I put the degrees on the bottom so they cancel. Then I can reduce these. Obviously, what goes into both of these? 3. So I get 11 pi over 6. Kabam. Now, number 2, I've got to, it's in my DNA, but I have to be evil. So I didn't even talk about coterminal, and I said dues. All coterminal means. So, if I say that's 0 degrees, you with me? If I want to look at you, I'm going to rotate by roughly maybe 40 degrees, or 45, let's say. You with me? If I then rotate by another 360, where will I end up looking? Still at you. So, how many total degrees did I just go? I went 45 plus 360. So what did I just do? What did I just rotate to? 45 plus 360. What is that? What's 45 plus 360? 405. So 405 degrees is what we call coterminal with 45 degrees because they both end up in the same place. Coterminal. They both end up looking the same way. So how do I get a positive coterminal angle? I take 129 and I just keep going another 360, yes? So 129 plus 360 degrees is 489 degrees. And then if I want a negative coterminal angle, I just go to 129 and then I go backwards 360 degrees. So what the hell is that? 231 degrees. Okay. Is that okay? So coterminal just means two angles that happen to end up in the same place. How many coterminal angles total are there for this one angle? Infinite, because I can go forward as much as I want, and I can go backward as much. Real quick. I just want to say this right now. Have any of you guys ever been? I think it's mostly like airports, but there are some like hotels and stuff. Kind of like exit from the parking lot that does like this. the corkscrew exit. You've seen them on movies and whatever. The where you have to kind of get out of the thing. Okay. As a student, I actually remember learning this and thinking, well, that is dumb as shit. Because I'm back. Hey, it's me again. You know, I hated that. But if I add one more dimension, not this, I'm sorry. If I add one more dimension, 3D like a real world, and I'm moving, if I look above, a car going in there looks like it's just going in a circle. But from the side, it's gaining height. So sure, when it rotates in the circle, it's like to the same place here, but it's gained height. So that helped me for some reason. I'm like, okay, it's okay that it kind of repeats angles, because maybe it's actually in another dimension, it's going up or going down if you want to leave the name. Okay. I have no idea if that helps anybody. That's just you, Jeff. All right, fine. Number 3, what's the very first thing? Oh, there, look. I used the word. It was me all the time. It was Jeff all along. What do I have to do first here? Sorry? Ah, beautiful. I gave it to you in degrees, like a complete dork. And I know I need it in radians for this to work. So arc length needs that, area needs that, and they both need the angle to be in radians. So it's currently in, dadgummit, Jeff, degrees. So if I want to convert that to radians, that's pretty quick, yes. Bam, bam, so I get 4 pi over 9. And then I just plug that into each formula. Now be really careful. I should have done this to you guys because this does it in the homework. If I would have said diameter of 38 inches, what would you put here?
110.
Yeah, so you would put 19 there, right? Be careful. In the homework, they're going to say diameter. Catch that, cut it in half before you plug it in. So here, though, I gave you the radius, 38, and the angle is 4 pi over 9. What's that going to be, math boy? It's going to be roughly 54, 53? How much? 53.05? And what's the units? Good, because arc length is just a length. It's not an area, it's not a volume. And then the area will be 1/2, throw in the radius. Good Lord, that's going to get kind of big. 4 pi over 9. What's that going to be, math boy? I don't know, man. It's going to be 1,000, I mean, I don't know. 2,000, holy shit. That's good. 2,050? Does that sound right? I'm crowdsourcing this. Oh, 2015? It was a good year. All right, let's see. I'm crowdsourcing. Do I have a calculator? I don't need no stinking calculator. I do. I really do. What'd you guys get? I'm sorry? Oh, you're pointing at your calculator. Okay, I appreciate that.
We have a disagreement. Oh, geez. A little better. 38 squared times 4. 5 divided by 10. And I get 1,008. Oh, yeah, 1,008, yes. So I think somewhere you forgot to cut it in half, maybe?
I left your calculator on like an asshole. Your poor battery's almost dead, and I'm like, you'll be. So 1,008 point stuff. What's the units on that? Square. Good. Okay. And then this guy, okay, I'm asking you for the area of a sector. Okay, for that, I need to know radius, and I need to know the angle in radians, yes? Did I tell you the angle? Directly, did I tell you the angle? No. Did I give you information that you could discover the angle? Yeah, because what's the arc length formula? Yeah, so S equals R theta. And what do we know? I know what S is, don't I? What is it? 21. And I know what R is? 7. So what's the angle? 3. 3 what? Radians. Kick ass. So area is 1/2 radius squared times the angle in radians. And that is roughly, what is it, 70 something? 73.55? Blah, blah, blah. What's the units? Good. Kick ass. Okay. I like it. Okay. There was something I wanted to show you. What was it? Damn it. I have forgotten. It's too bad. That's all right. Man. That's all right. It'll come back to me someday. I want to show you this real quick while my subconscious works on what I'm trying to remember. That's the area formula, correct? Does anyone see the arc length in that formula? Isn't R squared R times R? What's this? So did I tell you the arc length? Did I tell you the radius? So you could have done it in one step if you would have realized, oh, look at that. Arc length is in here. Did you have to do it this way? Obviously not. Look at us. We just got the answer, blah, blah, blah. But you could have done it here in one step. Okay. What was it? It was important. I forgot what it was. No, I'm gonna. Okay. It'll come back to me someday. I think that's enough for today. You guys upset if I let you out a little early today? Good, because I am. So I'll see you guys. Tomorrow we'll discuss when I haven't announced the quiz yet, have I?
No.
So tomorrow, what I think I'll do is I'll start with just the general review of everything we've done. Because what we're about to get into next is graphing trig functions. That's in chapter 8. Tomorrow I'll have because now I want you to do stuff like cosine of pi over 4, so you just try to work completely in radians to get more used to it. Okay, I'll see y'all tomorrow.
The paper that you put everything on.
Oh, sorry.
Yeah.
This year?
Oh, I see. You recorded it from here.
Yes. Yeah, I started doing that because there's like so much glare up
Yeah,
there.
this totally is